Alright guys, so we're going to talk about finding derivatives of logarithmic functions and exponential functions today. A little bit easier than the trig stuff, thankfully. Let's go ahead and begin here. Let's review logs and exponentials a little bit just to kind of re-jump your brains up into what logarithmic and exponential functions are. I think we all know what an exponential function is. It's where you have a number raised to the x power equals y. So for instance, if you had 2 to the x equals y, that would be an exponential function. Okay. Now a logarithm is the inverse of an exponential function. So we would write log here, and this number here, the a, is what we would call the base. So log base a, and since it's an inverse, over here the x is the input and the y is the output, but for logs it'll be reversed. Log y equals x. Okay. Logarithms are a really good way to find out what an exponent is if you don't know what the exponent value is. That will give you a certain y value. So that's what logarithms and exponential functions are. And since they're inverses, whereas an exponential function looks like this, logarithms look like this, because anytime you have an inverse function, no matter what it is, the two functions that are inverses always look like they're a reflection through that diagonal line there. Okay. Something to pay attention to is that for exponential functions, they have a horizontal asymptote here. So the exponential function cannot cross that line. So the range of an exponential function goes from y equals 0. It can't go to 0, and then up to infinity. Whereas for a logarithmic function, since it's flipped, it's not the range that's limited, but the domain. For the log function, it can't pass an x value of 0, but it can go to the right after that forever. Now, there's certain transformations you could do to these functions to flip them over or raise them up or move them left or right, which will change the domains and ranges. So the main thing I want you guys to pay attention to here is the fact that just basically what the graphs look like, that they're inverses of each other. Exponential functions have horizontal asymptotes. Logs have verticals. Those are some of the basic ideas. Just a nice context to know what we're talking about as we're doing this. And so there you have it. Now there's two kinds of special bases. The first one's the common base. So when a is 10, we call that the common log or the common base. So 10 to the x power can be rewritten as log xy. Notice they didn't put the 10 there. If they were going to put the base, it would be right here, but with a common base, they don't usually put the base there. So if you ever see a log where there's no number there, then that means the base is a 10. The other special base is the base known as e. It's called Euler's number. E is a value that is 2.718. No, it's not random. It's actually quite an amazing number. I'm not going to go into why right now, but basically, they call it the natural base because it works quite naturally with exponential and logarithmic functions. In fact, one of the reasons we like the number e is because of what we're going to see today in our lesson. It's quite amazing. The derivatives of these functions are extremely simple because of e. The derivatives of other exponential and logarithmic functions are unfortunately not as pretty to look at, but these guys are very simple. You're going to love derivatives of e to the x and ln, and they're very simple. All right, here's our first one then. Let's go ahead and take a look at it. So for the function ln of x, the derivative of that is 1 over x. Whatever the inside is, that's what goes on the bottom here. And there it is. Pretty simple, right? You can't get better than that. So let's go ahead. Actually, we will get better. I'll show you in a minute, but for now, we'll leave it at that. So here we go. Let's go ahead and do this one. Now, I wish, once again, like the trig ones, that the software I use would use parentheses, but they don't. So just know that there's parentheses here. So this is a chain rule. Once again, we have an inside function, and we have the outside function, which is the ln. Okay? So we're going to have the derivative of y then is going to be the derivative of the outside multiplied by the derivative of the inside. So the derivative of 4x squared is going to, that's the inside. Let's go ahead and do the derivative of 4x squared. That's going to be 8x. Now let's do the derivative of the outside, ln of x, right? Well, ln of something, right? Well, the derivative of ln is 1 over whatever the inside is. In this case, it's 4x squared. Okay, so we're going to multiply the 8x to the top. And we're going to reduce that, and then we'll be all done. So 4 goes into 8 4 times. And then this x on the top takes one of the x's on the bottom away. And there's our final answer, 4 over x. So the slope of this function can be found with the derivative, which is 4 over x. So for instance, what would the slope of this function be at x equals 5? It would be 4/5. All right, so here's some student practice. Once again, I wish they used parentheses, but they don't. So here's the parentheses. That's the inside function for number 1. And for number 2, the inside function is sine. So go ahead and see if you guys can find the derivatives of each one of these. Pause the video, and when you're done, you will see the solution. So the answer to number 1 is 3 over x. The answer to the bottom one, you probably stopped here, which is fine, but we have an identity for that. Cosine over sine is cotangent. Okay? So those would be the derivatives of those two expressions. Let's go ahead and move on to our next topic here. Let's talk about logs that have other bases. So here's how the logs of other bases go. So like if it's not ln, like let's say it's log base a instead. Well, here's how you do those derivatives. It's still 1 over x. You guys see that? It's still 1 over x, but you're going to multiply it by ln of a. Matter of fact, I really don't like the way this is written. If I were you guys, I would write it like this. So on your notes, maybe scribble that out and rewrite it like this. The x should really be in the front. So it's still 1 over x, just like it is for natural log, but then after that, you're going to multiply it by the natural log of the base as well. So not too bad, just a little bit more complicated. So let's do this one. So for this one, it's still going to be the derivative. We need to do the derivative of the outside times the derivative of the inside. The derivative of the inside is 10x to the 4th. The derivative of the outside, natural log of 2. Well, it's going to be 1 over the inside function times ln of the base, which is 2. This is the base, not this 2. This 2 is the base. It doesn't matter, but just so you guys know where I'm getting the number from. I'll draw a little arrow. So the inside function is 2x to the 5th. So if I were to try to simplify this, I would move the 10x to the 4th to the top, and we would have this. Now these can be reduced, right? So final answer would be 5 over x ln of 2. So guys, I mean, you could honestly just do it the same way you did the last problem. Just don't forget to put ln of the base on the bottom also, and you're going to get the same answer. It's the same exact process. You guys go ahead and pause the video here and give this one a try, and when you unpause it, you will see the solution. And there you guys go. So first we have the derivative of the outside here, then the derivative of the inside. Multiplying those together, we get this, and then reducing the monomial on the top with the monomial on the bottom, we get 3 over x, and the ln of the base stays there as is. Okay, so that is how you find the slope, derivative, or instantaneous rate of change of logarithmic functions. All right, let's go ahead and move on to exponentials. So here's another beautiful thing. When you're working with Euler's number, it's really quite interesting. The derivative of e to the x is e to the x. What a weird function. So in other words, the y value, right? So if I give you this function here, y equals e to the x. Let's say I asked you guys to find the y value when x equals 1. So let's plug in 1. You get e. Well, the derivative is also e, right? So if you plug in 1 to the derivative, you also get e. So at every point on the e curve, which looks something like this, at every point, The y value, whatever that is, the slope of the tangent line at that point is the same as the y value. So if we were at x equals 1 here, the y value would be e, and the slope of my tangent line would also be e. So that's kind of a really weird thing, but that's how they work. So, but to keep it simple, just know that the derivative of e to the x is just e to the x. So let's go ahead and put this to work. What if we actually do this? Well, this is a chain rule, and for these ones I wouldn't have parentheses myself usually. So when you're dealing with exponential functions, we do have an inside function and an outside function. For exponential functions, the inside function is the exponent. So this would be the inside function, and the e would be the outside function. So if it helps you, you can put parentheses, but just know that's typically not what anybody does, but it helps identify the inside versus the outside. So let's go ahead and do this. To find our derivative, we're going to do the derivative of the outside multiplied by the derivative of the inside. So the derivative of the outside, e to the power of whatever, is going to stay exactly the same. That's what the derivative of the outside is. The same thing as the original problem. But we do need to multiply it by the derivative of the inside. So the derivative of tangent, hopefully you guys are remembering, is secant squared. Okay? So derivative outside times derivative inside. The derivative of e is just itself. All right. So I want you guys to go ahead and try this problem. And just so you guys don't get confused, this whole thing is the exponent. So go ahead and try that, see what you guys get. Pause the video. When you unpause it, you shall see the solution. So here's the derivative of the outside function. Here's the derivative of the inside function. Something you guys might not have thought to do is put those parentheses, but that's important because if you guys didn't have the parentheses, let's see if I can get rid of those really quick. There we go. Let's say I didn't put those parentheses on there. Sorry, I'm struggling here a little bit with my technology. And let's say instead you just wrote it like this. The problem with writing it like this is it's a little bit unclear what you're multiplying. Are you just multiplying these two things together? Because that's actually what that would mean. So that would mean you're multiplying this times this and then adding 2. But with the parentheses, it means you're multiplying this times both of these. So this would actually be more like a distribution problem. So just something to keep in mind. All right. Anywho, let's go ahead and move on to another type of problem. So this kind of follows the same pattern as the other one. You guys remember that when we had ln of x, right, the derivative of that, I'll use that symbol for derivative. The derivative of that was 1 over x. And when we had another type of log with a different base, the derivative of that, well, it was the same thing. It's just that we had to throw an ln of a on the bottom with it, right? Well, the same thing applies with exponential functions, okay? So we found that when you have an e to the x, if you take the derivative of that, you just get e to the x. In the same way, when you have an a to the x, in other words, it's a different base, when you take the derivative of that, you still get the same answer, but it's going to be multiplied by ln of a, just like this one was. So that's the answer. Does it matter which one you put in the front? For this one, it doesn't really matter if you put ln in the front or back so much. Matter of fact, it's probably better. Yeah, let's do that. I think it'd be better if we wrote it like this. The reason why it's not good to put a number after the ln is because if you wrote this, if you wrote this, for instance, well, what that means is ln of 2x, which means you're taking the natural log of 2x. But if you didn't want that, if you wanted this instead, ln of 2 times x, you would need to write it like this. In this case, you're taking the natural log of 2 and you're multiplying the final answer by x. So it's different to multiply by 2 and then take the log than it is to take the log and then multiply by x. And so if you're not careful and you write this when you mean this or this, then you're actually doing something wrong. So it's just safer to avoid all that confusion if you just go ahead and make sure that you put the a to the x in the front. So I should have done that, but I was a naughty teacher. So this is probably a better way to write it, just so you guys know. All right, so, oops, okay. So let's go ahead and do some examples for that. Okay. So for this one, if I want to find my derivative, right, it's going to be another chain rule. So derivative of the outside times the derivative of the inside. The derivative of the inside is pretty chill. That's just going to be 6x squared. Derivative of the outside. How do you find the derivative of 5 to a power? Well, it's going to be 5 to the same power again. But this time we're going to multiply it by ln of the a. And the a is the base number. Like that. Okay? Now in this case, we can go ahead and we can, well actually, since these exponents, these bases aren't the same, you can't actually put the 5 and the 6x squared together. So a good way to write your answer, I guess, in the long run would just be to put 6x squared in the front, times 5, 2x to the third here, and then put the ln last, and that would be our derivative. You can't really combine or simplify anything. You're not allowed to multiply those together. Okay, so that's that. So same thing as the last one with e to the x. You just write the problem all over again, right? And you do the derivative of the inside, right? But you also have to multiply by ln of the base, since it's not a base of e. Okay? All right, so you guys go ahead and give this one a try. This is actually a double chain rule. It's an egg shell yolk egg white problem, right? It's a double chain rule. See if you guys can figure it out. Pause the video, and when you unpause it, you'll see the solution. Okay, so I've highlighted the parts. The yellow part is the innermost function, or the yolk as I've been calling it. The weird off-white color there is the outermost function, or the shell as I've been calling it. The green is the egg white, the medium function, right? It's not the innermost, the outermost is in the middle. So the derivative of the outermost function is in beige, or whatever this off-white color is here, orangish. So the derivative of the outside function is going to be exactly what the problem was originally, times ln of the base, which is 6. Multiplied by the derivative of the green inner function, the derivative of sine of 2x is going to be cosine of 2x, because that's what the derivative of sine is. And the derivative of the inside of that, the derivative of 2x is 2. And usually when it comes to the constants, they're going to throw that one up in the front, so I wrote my final answer like this. Okay, so that's a formula that will tell you the slope of this function at any given value of x, also known as the derivative. All right. So, a word of caution. There is a difference between a power function and an exponential function. Okay? So, for instance, this is what's known as a power function, x to the c. The derivative of those, that's the power rule that we learned. You take the power, you put it in the front, you take one off the front. So for instance, x squared. If I take the derivative of that, that's a power function. I would put the 2 in the front, and I would take 1 off of the power, right? That's the power rule. But what we learned today is about exponential functions. The difference between an exponential function and a power function is this. On a power function, the number is in the place of the power. But for an exponential function, the variable is in the place of the power. Okay? So they look similar, but they are different. So if I were to rewrite this, then it would look like this. That is a power function, whereas this is an exponential. I'm sorry, I think I said that backwards. This is an exponential function. This is a power function. To find the derivative of that, you do our power rule that we learned way back in our very first lesson. To find the derivative of this one, this is what we learned today. You're going to rewrite the problem and multiply it by ln of the base. So they look very similar to begin with, but they are completely different, and therefore the ways you find the derivatives or the slopes is very different. So you kind of got to be careful there. So what I would say here is what I want you guys to do is I would encourage you guys to go through here and find the derivative of each of these three problems. Some of them are power rules, some of them are exponential rules. So see if you can find the derivative of each one of these. Pause the video. When you're all done, you'll see the solution. Okay, so the first one has a constant multiplier in the front. Now, as you guys know, they don't change when you take a derivative. The constant multiplier just stays there. Okay? So we're going to leave the 5, but we do need to do the derivative of e to the x. Well, the derivative of e to the x is just e to the x. So the derivative of this expression is exactly the same thing as the original function itself. The next one, and by the way, that is an exponential function. Over here, this is an exponential function as well, but it doesn't have a base of e. So for those ones, we rewrite the function as usual, but we're going to put times ln of 5, ln of the base. This one over here is a power function, so we do the power rule where we multiply the 5 to the front and take 1 off the power to get 4. So there's your derivatives for each one of those. So we've learned about how to find derivatives of logs and exponential functions in this lesson. Hope it was good, and we'll talk to you guys in class. The end.